Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the lecture 2 of module 11. In today's lecture, we will learn about source spectra and the magnitude saturation. Especially we will be learning about why the magnitude saturation occurs for surface wave and the body wave magnitude scale. So the concept that we are going to cover today are source spectra, where we will see the convolution of two boxcar functions, and then corner frequency and the moment magnitude, and finally we will see the region of saturation of the surface wave and the body wave magnitude scales. Then finally we will have the summary of today's lecture. As far as the recap of previous lecture is concerned, we learnt about various magnitude scales and their general empirical forms, and also we have seen why and where the surface wave magnitude and the body wave magnitude scales saturated, and the region behind their saturation we will see today. The general form of earthquake magnitude is M is equal to log at base 10 A by T, where A is the amplitude of the signal and T is the dominant period. F H comma delta, this is the correction factor for the variations of the amplitude with earthquake depth, and C is the regional scale factor. Richter scale magnitude is represented by this formula, and Richter magnitude scale is generally valid for the region of the California. It was originally designed for the Southern Californian earthquake, and it was a local magnitude scale. So it is ML is equal to log A plus 2.76 log delta. Delta is the epicentral distance minus 2.48. Body wave magnitude scale is represented by M sub B. M sub B is equal to log at base 10 A by T plus Q H comma delta. Surface wave magnitude MS is equal to log at base 10 A by T plus 1.66 log at base 10 delta plus T 3.3. Body and surface wave magnitudes do not correctly reflect the size of large earthquakes and saturate about 6.2 and 8.3 respectively. So this is what we talked about in the previous lecture, that the body wave and surface wave magnitude scales do not reflect the correct size of the large earthquake. As the movement increases after a certain point, it doesn't reflect the movement in terms of the size correctly. Different techniques, body wave, surface wave, geodesy and geology, can yield different estimates. Then we learnt about moment magnitudes, that is M sub W is equal to log M naught. M naught is the seismic moment divided by 1.5 minus 10.73. It gives a magnitude directly tied to earthquake source processes that does not saturate. Today we are going to start with learning about the source model, and we are going to start with a simple model where the rupture starts from rest, that means from rest here, and then it propagates with a rupture velocity V sub r. They reach to its full velocity in time tau sub r. So you can see here the rupture starts from rest, and then it starts to increase and reach to final velocity, that is Vr, and then it stays there at moment m naught. And the timing it took to reach to that particular velocity is tau r, that is basically is your rupture time, tau r. So this is also known as Haskell source, and this particular simple source model, if you take the derivative of it, then it will become the boxcar function, something like this, and this mt will become m dot t, that is time derivative of the source time function, and it is varying from 0 to tau r. This is the rupture time here. Now if you look at this particular model here, you can see this is the fault, this is the finite fault here. You can see this is the start time of the fault, this is the ending point of the rupture. When the rupture starts here at this point, then the rays from this starting point reach to this particular station here in time r0 by v. V can be the velocity of p wave or the s wave, and as it reaches to the end point here, then the rays reaches to this station at time r by v plus L by VR. VR is the rupture velocity, and you can see the station is located at a back azimuth of theta from the starting point, and as soon as the rupture starts to move in the direction of rupture, then at different points the back azimuth will keep on changing, so theta is variable here. And if you denote it in terms of the time series, then it will become TR is equal to L in bracket 1 by VR minus cot theta by V. So the rupture time is basically proportional to cosine of theta here, and it is represented by boxcar time pulse. The displacement pulses ST can be represented by a convolution of boxcar functions with width tau r, that is rise time, and tau d, that is the rupture duration time, and this will yield a trapezoid. And you can see here the slip is started to increase and then it stays there at a particular value, and the time it took to reach to that particular value is tau d, that is the rupture duration time, tau d. And the seismic source time function A is equal to the rupture time, that is tau d, that will be convolved with tau r, that is the rise time of the rupture. So it is what represented here. You can see this is the rupture time here, this is the rise time here, though both are convolved, and in the convolved form it will be representing a trapezoid here, which is having the total width, that is tau r plus tau d, or tr or td. So our aim is to understand magnitude saturation of surface wave magnitude scale and the body wave magnitude scale, and we first have to briefly discuss about the source spectra. And the source time spectrum of an earthquake can be approximated by a slip function, that is basically shown here, and we have discussed about it. And the source time spectrum can be represented by the convolution of rise time and the rupture time, and this source time function can be represented by the convolution of two boxcar time functions. This is what it is represented here, and the convolution in time domain is the convolution, but in frequency domain it is simply the multiplication of both the functions. And when you take the transform of the boxcar function of height 1 by t over a length capital T, so this boxcar function transform will become sinc function, that is sine omega t by 2 divided by omega t by 2. So in case, let's suppose if you write down the sinc function f of x, that means it is sine of x by x. So when the two sinc functions convolve with each other, then you can take their FFT, and then in the FFT form these sinc function will turn to the boxcar function, and these boxcar functions, when they convolve with each other, then give this sinc square x function. So as I told you, this AF source time function is TR, that is the rise time, and convolve with TD, that is the rupture time. And you can write down, so this thing is in the time domain. When you convert it into the spectrum, then you can simply multiply them, and that will become A omega is equal to m naught sine omega TR by 2 by omega TR by 2 sine omega TD by 2 by omega TD by 2. So basically this A omega is just the multiplication of TR and the TD in the frequency domain. So TR and TD are the rupture and the rise time, and the above equation is used in the form of logarithm here. So you can take logarithm of both the side. If you approximately talk about the sinc function, this sinc function is basically nothing but sinc x, that will be equal to 1 if x is less than 0. Otherwise you can think about it as 1 by x when x is greater than 1. So basically if you look at, let me skip some slides here, and you can see here the sinc function basically looks in original form, it looks something like this. It should follow this path, but the approximation that we just talked about can be written something like that. If x is less than 1, then it will be 1, and if x is greater than 1, then it will be 1 by x. So it is not a very good approximation, but it works well here. So when we are talking about this particular source time function, that is just the multiplication of TR and TD, and it is multiplication of two sinc functions of TR and TD, then let's talk about this. So basically when you will take this particular thing, so if you take the logarithm of it, so it will become log of mod of A omega, that will be equal to log of m naught plus log of sinc omega TR by 2 plus log of sinc omega TD by 2, right? So you need to find out the values at which it will give us certain corner frequencies. So let's suppose consider that TR is greater than TD, that means rise time is greater than rupture time, and that we are assuming here. And if this is true, and then we basically consider that the angular frequency is less than 2 by TR, then what will happen? You can see that omega TR by 2 is less than 1. So in that case, this particular term omega TR by 2 is less than 1, so this will become 1. So likewise, if you consider the omega TD by 2, since we know TD is even less than TR, so this omega TD by 2 will also be less than 1 here. So in that case, if we take log AW, that is equal to log m naught, and this is the first sinc function, log of first sinc function, that is log of omega TR by 2, and omega TR by 2 as we know is less than 1 for omega less than 2 by TR, then it will become 0 log of 1, and it will also become log of 1, that is equal to 0. So this particular thing will become log of m naught at omega less than 2 by TR. When omega is greater than 2 by TR and less than 2 by TD, then in this case sinc of omega TR by 2 will be equal to 2 by omega TR, since we know that x is greater than 1 here. So the value of this sinc function will be 1 by x, so it will be 2 by omega TR, and sinc of omega TD by 2, that is basically less than 1, then it will become equal to 1. So in that case, log of A omega will be log of m naught plus log 2 by omega TR plus log of 1 here. And this log of 2 by omega TR can be written something like this, that is log of omega TR by 2 to the power inverse, and this inverse will go in the front, then it will be minus 1 log omega TR by 2, and then finally you can write it like this. Now if we consider omega is greater than 2 by TD, then both the sinc function will give the value of 1 by x, that means 2 by omega TR and 2 by omega TD. And then when you will put that into this equation here, then it will become log A omega is equal to log m naught plus log in bracket 2 by omega TR and 2 by omega TD. And when you will expand it further, then it will become log of m naught minus log TR TD by 4 minus log omega square log m naught minus log TR TD by 4 minus 2 log omega here. So as I told you previously, the sinc function is the one that follows this particular curve here, but the approximation we can make, if x is less than 1, that is equal to 1, and if x is greater than 1, that will be equal to 1 by x. So this is the approximation we took. And finally, for tr is greater than td, the log of a omega will become log of m naught. When omega is less than 2 by tr, it will be log m naught minus log tr by 2 minus log omega, when omega is in between 2 by tr minus 2 by td. And then this will become, for the omega greater than 2 by td, it will become log of m naught minus log tr td by 2 minus 2 log omega. So the spectrum is flat for frequencies less than first corner, goes as 1 by omega between the corners, and decays as 1 by omega square for the high frequency. So you can see the values of the spectrum. If the corner frequency is 2 by tr, less than 2 by 2 tr, then it will be a flat spectrum that will be having the values this, and in between 2 by tr and 2 by td, it will be proportional to 1 by omega, and for frequencies greater than 2 by td, it will be proportional to 1 by omega square. So this is what it is here. So log of AWs will be flat up to 2 by tr. In between 2 by tr and 2 by td, it will be having the slope 1 by omega, and after 2 by td, that means for the frequencies greater than 2 by td, the slope will be 1 by omega square here. So this path it will follow. So thus the spectrum is parameterized by 3 factors: seismic movement, rise time, and the rupture time. So you can see here it is being parameterized by 3 factors. That is correct. We have seismic movement, we have rupture time, and we have the rise time here. So the key points are, we can use other source spectral model to add third corner frequency to this model representing the effect of the fault width and yielding an omega by 1 by omega cube segment at high frequency. So you can even have one more segment of slope 1 by omega cube for more complex models, and that will add the third corner frequencies to the model. As a result, the interpretation of observed earthquake spectra depends somewhat on the source model. Seismic movement is the scale factor for the spectral amplitude at low frequencies, that is omega tending to 0. This is the reason why it is called as static movement. So static movement m naught, that will be equal to mu d bar s, where d is the slip, s is the area, or you can say the rupture area, and that will further be equal to mu d bar f l square, where f is the shape factor and the square of the dimension, that is the l square. The rupture time needed for the rupture to propagate along the fault is approximately Tr is equal to L upon Vr. This Vr can lie in between 0.6 times shear wave velocity to 0.9 times shear wave velocity. So here they have taken a value in between L upon 0.7 beta. So what we are assuming here that the rupture velocity is about 0.7 times the shear velocity. The rise time needed for dislocation to reach to its full value at any point on the fault has been predicted to be about mu d bar by beta delta sigma. So delta sigma is the stress drop here, beta is the shear wave velocity, and d bar is the slip, and mu is the shear modulus, and that can be further equated to 16f under root divided by 7 beta pi 1.5. So where delta sigma is the stress drop in the earthquake. So as the fault length increases, the seismic moment, rupture time, and the rise time increase. The moment m naught determines the zero frequency level, which rises as the earthquake becomes larger. The empirical relations between slip fault length and the moment is basically depicted here. You can see the surface rupture length and the average displacement are proportional to each other for the strike slip, reverse and the normal fault, and it basically give you a empirical relationship between the log of average displacement and the surface rupture length. So it can basically provide a empirical relationship here. Likewise, there also it is being provided here. And now, as you know, we have talked about the source model, a simple source model, where the corner frequencies were 2 by TR and 2 by TD. So basically, as the movement increases, these corner frequencies move in the leftward direction like this. So you can say, like, as the earthquake get larger and larger, the movement increases, and when the movement increases, then these frequencies will go to the left, will decreases. So that means the TR and TD time will increase, and subsequently 2 by TR will decrease and 2 by TD will also decrease. So you can see that basically here, you can see here the movement is increasing of the order of 10. So you can say the here 10 to the power 18 the value of m naught here, and it is increasing to 10 to the power 28 here for the larger earthquakes. As you go up and up, the movement is increasing. So when the movement increasing, that means the size of the earthquake is increasing and the corner frequencies will reduce. So the source spectra will basically squeeze as you go to the larger earthquake. So you can see these corner frequencies are basically shifting to the left, right? Likewise, there is another corner frequency here that is shifting to the left, likewise as you go up. So also that is shown here, the length of the fault is basically more as you go up in this direction. So larger earthquakes basically having is occurring on the larger fault, and it will basically give you the larger movement, and then the corner frequency will move to the left. So this is what it is written. We are going to find out the reasoning behind the saturation of the surface wave magnitude scale for the magnitude values for the large earthquake, that means for more than 8.2. And you know that the surface wave magnitude scales are measured at a period of 20 seconds. That is mostly for the Rayleigh waves. The amplitude of the surface waves are larger at 20 seconds. So basically the magnitude of the surface waves depends for the amplitude of the 20-second period wave, and it also depends on the spectral amplitude at this period. So for earthquakes with movements less than 10 to the power 6 dyne centimeter, a 20-second period corresponds to the flat part of the spectrum. So ms increases with the movement. So you can see for less than 10 to the power 26, for less than 10 to the power 26, for this part of the spectra, the size, the value of the movement lies in the flat part. So you can see up to this value, this particular movement is basically lying in the flat part of the spectra. So it will give you the correct value up to 10 to the power 6. However, for larger movements, 20 second is to the right of the first corner frequency. So as you go above the 10 to the power 6, then it will finally fall into this particular portion. So this basically tells us that it is not going to give you the correct estimate of the size of the earthquake here. So once the movement exceeds the 5 into 10 to the power 27 dyne centimeter, the 20 second is to the right of the second corner, that means on the slope of 1 by omega square portion of the spectrum. Thus ms saturate at about 8.2. So even if the movement increases, but the movement is increasing, but it will basically leave the second corner frequency, and it will not give you the correct estimates of the movement of the earthquake, or you can say the size of the earthquake or surface wave magnitude. Likewise, same is true for the MB, but we know that the body wave magnitude scale, that depends on the amplitude at the period of 1 second, because this period is little shorter than the 20 second for the surface wave magnitude scale. The MB saturates at lower moment, that means at about 10 to the power 25 dyne centimeter, and remains about 6 even for much larger earthquakes. So here is what they have shown us. So for 1 second the movement is basically this thing, and it will be giving the correct value. It will lie in the flat and the 1 by omega corner frequency values up to here you can see, and but if you go much above than that, then it will basically go off the 1 by square omega square slope of the spectrum. So it will not give you the correct value of the earthquake. Those are having the magnitude higher than 6, and similar saturation effect occur for other magnitude scales which are measured at specific frequencies. So here is the demonstration of saturation of body and the surface wave magnitudes. So you can see here from the observations it was found like here the solid circles, solid filled circles are denoting the earthquakes that are happening on the interplate boundaries, and the hollow circles are representing the earthquakes happening on the intraplate boundaries. So you can see here on the y-axis the movement is given, on the x-axis the surface wave magnitudes are given, and as the movement increases up to 10 to the power 28 around, after which it gets saturated. And for here also it gives the relationship for the rupture area and the magnitude of surface wave that is given on the x-axis, and as the surface area increases after a certain value it gets saturated and it doesn't increase further. So this is what it is written: MS saturate even as the movement and the fault area increases. Open and the closed circle denote the intraplate and the interplate earthquakes respectively. For earthquakes above about 10 to the power 28 dyne centimeter, MS saturates even for progressively larger fault areas and seismic movements. As a result, MS is not a useful measure of the size of very large earthquakes. So this is the summary of today's lecture. The relations between the movement and various magnitudes arise from the spectrum of radiated seismic waves. Seismic movement is the scale factor for spectral amplitude at low frequencies, that is omega 10 to 0. This is the reason why it is also called the static movement and defined as the m naught is equal to mu ds, that is equal to mu df L square. Here the fault area is written in terms of shape factor f and the square of a dimension L. The rupture time needed for the rupture to propagate along the fault is approximately Tr is equal to L upon Vr. The rise time needed for dislocation to reach its full value at any point on the fault has been predicted to be about Td, that is equal to mu d bar by beta delta sigma is equal to sigma 16 f 1 by 2 divided by 7 beta pi to the power 1.5, where the delta sigma is the stress drop in the earthquake. The moment m naught determines the zero frequency level which rises as the earthquake becomes larger. Once the moment exceeds about 5 into 10 to the power 27 dyne centimeter, 20 second is to the right of the second corner on the 1 by omega square portion of the spectrum. Thus MS saturates at about 8.2 even if movement increases. MS saturates even as the movement and the fault area increase. MB saturates at a lower moment, that means at about 10 to the power 25 dyne centimeter, and remains about 6 even for much larger earthquakes. So this is the references, and that is all for today's lecture. Thank you very much. Bye bye.